So that's all for as for the expected value. The second parameter we are usually interested in is the variance. So let's consider also the similar cases. So the first case is when you want to find a confidence interval for the variance of a normally distributed sample when the expected value is given. So here also parameters are mu and sigma, and mu is supposed to be known, supposed to be given. In this case, the formula for the of a confidence interval for the variance is so as follows. Here you can see the quantiles of the chi-square distribution. So in denominator of both formulas, of both endpoints, you see the quantiles of chi-square distribution. This is also a distribution similar to the student's distribution that has no its own physical meaning, but is only used as an auxiliary distribution in mathematical statistics. So when you need the quantile, you also Google for the table and you find the quantiles there. As you see here, endpoints differ in the level of the quantile. So the left endpoint has the quantile of the level 1 minus alpha over 2, and the right endpoint has the quantile of the level alpha over 2. This is the only difference. So the more common situation is a situation when you don't know mu, when the actual value of mu is unknown. And so in this situation, you do what? You use the sample variance. So you calculate the sample variance according to the standard procedure, according to the standard formula. So in this formula, Sn squared is a sample variance, the sample variance. And you see that, be careful, n minus 1 in the numerator of this fraction is a coefficient. So S squared is multiplied by n minus 1. And n minus 1 in denominator is the parameter of chi-square distribution. So this is a chi-square distribution with n minus 1 degrees of freedom. So in denominator, n minus 1 is not a coefficient. It is a parameter of chi-square distribution. So, and here you also see that left and right endpoints of the confidence interval differ in the level of the quantile. So let's now apply the formula for variance, so confidence interval for the variance. Let us say that we are measuring the same value with some measuring tool. Let's say this is a temperature. Air temperature in this room, for example. I measure it with the same tool, with the same thermometer, 9 times. And the results are as following. These are degrees Celsius. So 19.8, 21.2, 18.6, 20.4, 21.6, 19.8, 19.9, 20.3, and 20.8. And we are to find the confidence interval for unknown variance. So let's say the 95% as usual, or maybe let be not 95 but 90%. 90% confidence interval. Confidence interval for unknown variance sigma squared. So, what is to be done? The first step is to find sample mean. So x bar, these are xi's, x bar is 1/9 times sum of these values. If we do all this and all calculations, we'll get 20.27. So sample mean is 20.27 degrees. Then we are to find here not the sample variance, but sum of squares of differences. So we are to find sum for I from 1 to 9 of squares of differences between xi and x bar. So this is like 19.8 minus 20.27 squared plus and so on up to the last one, to 20.8 minus 20.27 squared. So sum of squared differences. This is equal to 6.3. And then I will need two quantiles of the chi-square distribution. So as I'm asked to find 90% confidence interval, then 1 minus alpha is 0.9, and that means that alpha is 0.1 and alpha over 2 is 0.05, and 1 minus alpha over 2 is 0.95, and I need two quantiles of the chi-square distribution with a number of degrees of freedom is equal to the sample size minus 1. Sample size is 9. I have 9 observations. So 9 minus 1 is 8. 8. Quantile of the level 0.05 is equal to 2.73. And the quantile of the level 0.95 is equal to 15.51. So the confidence interval is, so we need to take this sum of squared differences and divide it by the lower quantile. This is, no, by the higher quantile. This is the left endpoint. So I divide 6.3 by the 15.51. And the right endpoint is the quantile divided by the squared sum of squared differences divided by the lower quantile. So by the 2.73. And so if we do these two divisions, we'll get 0.4 here and 2.3 here. So the answer, the final answer is that unknown variance is from 0.4 to 2.3 with probability 0.9. So that is how it works for the variance. So no, as for the sample mean, when we find confidence interval for a sample mean, it is for a mean value, for the expected value, it is sample mean centered. So we have sample mean plus and minus the same value, and here we don't have any additions, only divisions, and so we cannot say that this interval is sample variance centered or something like this. It's just we get the endpoints and we cannot present it in the form something plus minus something else. So that's it. Then, when dealing with mean values, we are usually interested in difference in means. So difference between μx and μy. And when we deal with variances, we usually try to estimate not the difference of variances, but a proportion of variances. So sigma y squared divided by the sigma x squared. And so in this case, the formula for the confidence interval is given, and we are to apply quantiles of the third auxiliary distribution, the Fisher distribution. So I won't repeat the same phrases, just it is another auxiliary distribution in mathematical statistics. So quantiles of the Fisher distribution are usually provided in tables only for small levels, so only for alphas close to 0. That is why if you need the quantile of the high level, of the level equal to close to 1, so you are to divide. So if you, for example, if you need the quantile of the Fisher distribution of the level 0.99, you are to find the quantile of the level 0.01, and so you are to divide 1 by this quantile. So quantile of the level 0.99 is 1 divided by the quantile of the level 0.01 and vice versa. So that is how you can find quantiles for the right endpoint of this confidence interval. The third parameter that is usually estimated with the confidence interval is what we call a proportion, a population proportion, or a probability of some event. So actually we can look at this situation from two different viewpoints. So either we can say that what we are estimating is a proportion. So, for example, a proportion of voters who support some political party, or proportion of defective items in production of some factory. So there is a population, all voters or all items produced by the factory, and so there is a proportion of voters who support our party, proportion of defective items, and so we want to estimate this unknown proportion. Or from the other point of view, we can say that what we are estimating is a probability. So we can say that there is a probability that a random person will support this party, or a probability that a random item is defective. So how this can be done? So we calculate sample proportion. We calculate the sample proportion by dividing number of successes in our series of observations by the number of observations. So, for example, you go out to the street and you ask random people, will you support this party? And they answer either yes or no. And you divide number of those who are in favor of your party by the number of people you have asked. And so these are m and n respectively. And what you get is called the sample proportion. Or you choose items at random, and you for each item you look if this item is defective or not, and so then you divide m number of defective items by n number of items observed, and so also this is a population, the sample proportion. So p hat is a sample proportion. This is a point estimator, as you know, of unknown population proportion. And the formula of the confidence interval is given. So here you use quantiles of the standard normal distribution. So Z is a quantile of a normal distribution, and instead of variance, of the sample variance, you have this formula, this expression, p hat times 1 minus p hat divided by m. And the last situation we will discuss is a confidence interval for difference of two proportions. So you have two populations, for example, voters in one city and voters in the other city, or you have items produced by the first factory and items produced by the second factory. So you have two populations, you have two population proportions, and you are interested in their difference. So in this case, you calculate two sample proportions, and the formula for the confidence interval also is given. So you have a little bit more complicated expression for the sample variance. So what you see under the square root. So it's actually everything is like here, but just you have differences of two p hats, differences of two sample variances, and difference of p1 and p2 of two population proportions as an parameter to be estimated. So these cases I have shown you are the most common. They cover, I would say, 99% of all problems of interval estimation. So even without any knowledge about how to derive a formula for the confidence interval, you can solve many problems we solve in our real life, just applying these formulas I have given. As our time is limited, I will not show you an example for of a confidence interval for a single proportion, for a single probability, but let's find a confidence interval for difference of two proportions. So let us say that there are two areas, area A and area B, and there is a survey the survey is conducted, is done to find how local people are satisfied of the work of the public transport in their areas. And so in area A, in the area A, 168 people, random people, were asked, and 127 of them are satisfied with the work of the public transport in their area. And in the area B, 207 people were asked, and 132 of them are satisfied with the work of the public transport. So, and we are asked to find 95% confidence interval for the difference of two proportions. So P1 is a proportion of those who are satisfied in the area A, and P2 is a proportion of those who are satisfied for the area B, and we are asked to find 95% confidence interval for P1 minus P2 for the difference of two proportions. So the first step is to find sample proportions, so P1 hat and P2 hat. So we see that M this is M1, this is N1, this is M2, and this is M2. So P1 hat is M1 divided by N1, so is 127 divided by 168, that is approximately 0.756, and P2 hat is M2 divided by N2, that is 132 divided by 207, and this is approximately 0.783. So when we are constructing confidence interval for a proportion or for a difference of two proportions, we use the normal quantiles of the standard normal distribution. So we will need quantile of the level 1 minus alpha over 2. So we say that alpha is 0.95 and 1 minus alpha over, 1 minus alpha is 0.95, I'm sorry. 1 minus alpha over 2 is 0.975. The quantile of standard normal distribution, we need the quantile of the level 0.975, that is equal to 1.96. So now we are ready for the interval itself to collect all the numbers we have already got. So P1 hat minus P2 hat is 0.756 minus 0.683, then minus, and here we have, instead of the sample variance that we have for when we are constructing confidence intervals for the mean value, for the unknown expected value, here we have this big square root, and here we have P1 hat minus P2 hat, P1 hat times 1 minus P1 hat, so 0.756 times 1 minus 0.756 divided by the sample size of the first sample by the 168 plus P2 hat 0.683 times 1 minus P2 hat divided by the sample size of the second sample by the 207. And then multiplied by the quantile 1.96 in our case. So, and this is the left endpoint. And here we have the same, but with plus here. So and the probability is 0.95. So now it's time to simplify. It's time to simplify these numbers. After simplification, we'll get what? So the difference of sample proportions is 0.118. So this expression, the square root multiplied by the quantile, is equal to 0.02922. No. And this is equal to 0.95. So, and finally, the right and left endpoints, the left and right endpoints of the interval are 0.0258 and 0.2102. So this is the interval. So average sample, sample difference, yes, the difference of two sample proportions of those satisfied with the public transport for area A and area B is this one. So we see that approximately 12%. So difference is 12%, significant difference. So for the area A, approximately 75.7% are satisfied, and for the area B, approximately 68.3%. And difference is 11.8%. And so we can say that real difference, so this 12% is what we get from our sample, and real difference of two population proportions, is with high probability somewhere from this to this value. So from 2.58% to 21.02%. So the interval is wide. So from 2.5 to 21. So we see that this estimation is not so very accurate, and this means that sample size that we have here is not enough. Is not enough to get more, more accurate estimator, to make more accurate estimation of what we have here, of this difference.